Unit 2, Worksheet 5, Multiple Representations of Motion. For each of these 8 problems, given one motion representation, supply the missing motion representations. In this class, we have talked about 4 different ways to represent motion. One way is with a position versus time graph. We also talked about representing motion with a velocity versus time graph. We've talked about representing motion by using written words as the written description. And we have also talked about how we can represent motion using a motion map. Each of these 8 problems will provide one way in which an object can be represented using one of our representations of motion. And then it is our job to fill in the other 3. For this first problem, we're actually given the position versus time graph that's already filled in, and we need to identify the other parts and other ways to represent this motion. So for this first problem, what I am noticing is there aren't any numbers here to help me out with saying, hey, I'd start at this point. However, one thing that I know is down here is always going to be my position of 0 at the origin. So I have some positive starting position. So when I write my written description, what I'm going to do over on the right, the object starts at some positive position. If I know exactly what that starting position is, I should write down what that position is. But I don't, so I'm just going to write down that it is some starting position. Then I can see that this object is increasing in my position. What that means is the object travels to the right. And because that slope is constant, I'm going to write that the object travels to the right at a constant velocity. I don't know exactly how long this is traveling for, so I'm going to leave that off. In the next region of the graph, the position does not change. So I can say that the object remains at rest or does not move. Now, one thing that I can also see is that this length between these 2 points, between my 2 dashed lines, is going to be very similar to that distance that I have right over here. So I can assume that that's going to be the same amount of time. The object remains at rest for the same amount of time. Then in this last region, the position looks like it is decreasing. The object travels left, and because I can see that that slope is going to be steeper, even if it's a negative slope, I can say that the object travels left at a faster speed. Now, what I'm doing here is, in that second point, I said constant velocity, because it is a constant velocity where I do care about that direction of travel. However, because I am comparing the magnitude of these slopes here, I'm not really interested in the direction. So that's why for this last little bit, I'm saying speed. The object travels faster. It has a steeper slope here than it does over here. That is one of the times where speed is going to be a better way to represent 2 objects' motion than velocity. Is when we just want to talk about how quickly they are moving, but we're not too interested in the direction. So for our velocity versus time graph, I'm going to be looking at that same region that I have up above. So in this region is where I'm going to translate that down to my velocity versus time graph. I know that this is going to be a positive velocity, but that's all I really know. So I'm going to have a horizontal line saying that my constant positive velocity is constant. It is not going to be changing. In the second region right over here, my slope is 0. So I'm instantly changing it down to my velocity of 0 in that time region. In the last region of the graph, I have a negative slope. And because I know that slope is going to be steeper, I am going to put it further away from my x-axis than that positive slope was. So this is a tiny little bit of distance here. This is a bigger amount of distance. That should correspond to the magnitudes of the slopes that we're seeing on the position versus time graph above. Now, the third way that has not been represented yet is going to be our motion map. Our motion map, I know that at my starting position, it's not going to be here at 0 meters. So I'm going to put maybe just a little bit over where I begin, or my 0-second interval. I know that this object travels to the right, so after some amount of travel, it might end up over here. And I draw my velocity vector to show it travels to the right. I also want to show that that velocity is going to be constant, so I'm actually going to do 2 seconds for these intervals. So it's still traveling to the right. I'm going to say each one of these time intervals over here is going to be 2 seconds. That just makes it easier for me to draw just 2 dots per time interval. I've now had it travel to the right or in the positive direction for 2 seconds. Now I'm going to need to make sure it rests for 2 seconds. At 2 seconds, I'm not putting an arrow on, so it doesn't move. At 3 seconds, I'm not putting an arrow on, so it doesn't move. 4 seconds, however, it's going to start moving again to the left. Now, I want to show that it's going to be changing a greater amount of position in that same period of time. So that way I'm going to be making my arrow a little bit bigger and putting my dot a little bit further on. So let's say it moves 3 ticks. So even though my arrow is pointing in an opposite direction, which does tell me I have a lower slope, a lower velocity, which is going to correspond to a lower slope, it's going to be a longer arrow because it's telling me it's moving faster in this direction. And then I will have that represented again. And then who knows how far that's going to keep traveling after this is over. These are 3 different ways that we can represent that provided motion map that was given to us in this problem, with our written description describing in real-world terms what is happening in that position versus time graph. We can look at the slope of the line in our position versus time graph in order to figure out the velocities in those same regions. And we can also go from a position versus time graph down to our motion map in order to set up a motion map that represents our motion of that position versus time.